1. Antimatter breakthrough, new class of particles discovered at LHC. 2. CERN's breakthrough, first evidence of CP violation in baryons explained. 1. Antimatter breakthrough, new class of particles discovered at LHC. What if the universe we know is just a cosmic accident? Imagine a world where every star, planet, and living being vanishes in a blink, because matter and antimatter, born equal in the Big Bang, annihilated each other. But here's the twist: somehow, our universe survived. Now, scientists have uncovered a clue that could explain why. At the heart of this mystery lies a recent breakthrough from the Large Hadron Collider, LHC, where researchers have spotted a strange behavior in antimatter particles that might finally help solve the riddle of why matter dominates everything we see. The discovery centers on a class of particles called baryons, those triplets of quarks that make up protons and neutrons, the building blocks of atoms. For decades, physicists have known that matter and antimatter aren't perfect mirrors. Tiny differences, known as CP violations, cause some particles to decay at slightly different rates than their antimatter twins. But until now, these discrepancies were only observed in mesons, which are made of quark-antiquark pairs. The LHCb experiment has now confirmed that baryons, too, exhibit this odd behavior. Specifically, baryons containing an up quark, a down quark, and a heavier beauty quark decay more frequently than their antimatter counterparts. This is a big deal because baryons are the stuff of ordinary matter, the atoms in your body, the air you breathe, and the stars in the sky. But here's where it gets controversial: the standard model of particle physics already predicts some level of CP violation. The problem? The amount observed here isn't enough to explain the universe's overwhelming matter-antimatter imbalance. As Jessica Turner, a theoretical physicist at Durham University, puts it, the result fits expectations, but it doesn't solve the bigger puzzle. In fact, this finding aligns with earlier measurements in quark interactions, which still fall short of explaining why we exist at all. And this is the part most people miss: this experiment isn't just a technical triumph, it's a stepping stone toward uncovering physics beyond the standard model. How did they do it? The LHCb experiment is essentially a high-tech time machine. By slamming protons together at nearly light speed, it recreates conditions from the early universe. Each collision generates a shower of particles, and the LHCb's 6,000-ton detector acts like a 4D camera, capturing every decay and interaction. It's like watching a movie frame by frame, says Vincenzo Vagnoni, spokesperson for the team. We can rewind the action to see exactly what happened. This precision allowed them to spot the minuscule decay rate difference between matter and antimatter baryons, a feat described as amazing by Nobel laureate Edward Witten, who wasn't involved in the study. The implications? While this isn't the final answer, it opens new doors. Theorists like Vagnoni believe the key lies in undiscovered particles or forces that existed in the universe's first moments. We're hunting for cracks in the standard model, he explains. If we find even a tiny mismatch between theory and observation, it could lead to a breakthrough. The LHCb team plans to collect 30 times more data in the coming years, probing rarer decays that might hide larger clues. Will they find the missing piece of the puzzle? Or will the universe's greatest secret remain just out of reach? So, what do you think? Is this a mere footnote in the quest for understanding, or the start of a revolution in physics? Drop your thoughts in the comments, because the story of why anything exists at all is far from over. 2. CERN's breakthrough, first evidence of CP violation in baryons explained. For the very first time, groundbreaking experimental evidence has emerged from CERN's LHCb collaboration, revealing the violation of charge parity, CP, symmetry in baryons. This significant finding aligns with the standard model of particle physics and may impose limitations on theoretical frameworks that seek to expand the standard model to account for the observed imbalance of matter over antimatter in our universe. Current cosmological theories suggest that the Big Bang initiated a colossal release of both matter and antimatter, most of which quickly annihilated each other. Surprisingly, the universe we observe today is predominantly composed of matter, with only trace amounts of antimatter detectable. This puzzling surplus of matter remains unexplained by the standard model, presenting a profound enigma in the field of physics. Back in 1964, a pivotal experiment conducted by James Cronin, Valentine Fitch, and their team at Princeton University investigated the decay of neutral K mesons. Their findings demonstrated that the weak interaction could violate CP symmetry, suggesting that matter and antimatter might not behave identically. For their groundbreaking work, Fitch and Cronin were awarded the Nobel Prize in Physics in 1980. Following this, the renowned Soviet physicist Andrei Sakharov proposed that if CP violation were amplified at extremely high mass scales during the early universe, it could have played a crucial role in creating the matter-antimatter asymmetry shortly after the Big Bang. Since then, numerous instances of CP violation have been documented in various mesonic systems. This phenomenon has become an integral aspect of the Standard Model, characterized by the Kabibo-Kobayashi-Moskawa (CKM) matrix, which outlines the probabilities of quarks from different generations transforming into one another through weak interactions, a process known as mixing. A minuscule effect. Despite these advancements, the CP violation observed through the CKM mechanism is significantly less than what would be necessary to account for the leftover matter from the Big Bang, as explained by Xueting Yang from Peking University in China. In Big Bang theory, the ratio of remaining baryons to the number of photons produced when baryons and antibaryons collided and created two photons should be approximately 10^-10. However, the Standard Model predicts this ratio to be only about 10^-18. Moreover, CP violation had not been previously detected in baryons. Yang, a member of the LHCb collaboration, notes, the theoretical predictions for baryon decay are quite uncertain. Calculating these decays is far more complex than for mesons due to interactions with the strong force. Baryons, which primarily consist of protons and neutrons, constitute nearly all the hadronic matter in the universe, leaving open the possibility that discrepancies between baryonic CP violation and Standard Model predictions could provide insights into this mystery. In their recent study, Yang and his colleagues at LHCb focused on the decays of beauty, or bottom, baryons and their corresponding antibaryons. These heavier relatives of neutrons contain an up quark, a down quark, and a beauty quark, and were generated during proton-proton collisions at the Large Hadron Collider between 2011 and 2018. These baryons and antibaryons can decay through various channels. For instance, one decay pathway involves a baryon transforming into a proton, a positive K meson, and a pair of pions, while the corresponding antibaryon decays into an antiproton, a negative K meson, and a pair of pions. CP violation is expected to create an asymmetry in these decay processes, prompting researchers to search for evidence of this asymmetry in the particle counts detected at different energies from all collisions. Standard Model holds strong. The research team discovered that the CP violation observed was in line with the Standard Model and showed a significant deviation from zero at a confidence level of 5.2 sigma. Yang remarked, "The precision of our experimental results surpasses what theoretical predictions can currently provide." Other researchers within the LHCb collaboration examined alternative decay channels of the beauty baryon, noting, their findings remain consistent with CP symmetry. While CP violation should also be present in these decay channels, we currently lack sufficient statistical data to assert that the deviation exceeds 5 sigma. The existing data do not eliminate the possibility of extending the current Standard Model, according to Yang, as none of these extensions offer precise predictions regarding the expected level of CP violation in baryons. As the LHC enters its third operational run, researchers are optimistic about gathering more information, particularly concerning the intermediate particles involved in the decay processes. Yang stated, "We may be able to provide measurements that are more relevant for theoretical comparisons and could impose constraints on the Standard Model's predictions for CP violation." This research is detailed in a paper published in Nature. Tom Browder from the University of Hawaii commented, "This is a significant paper, an old type of CP violation observed in a new system." Theorists will strive to interpret these findings within the framework of the Standard Model, and while there have been initial attempts, uncertainties arising from this strong interaction hinder precise testing. Nevertheless, these results could potentially help refine extensions of the Standard Model, including CP-violating decays involving dark matter, as proposed by the late Ann Nelson and her colleagues at the University of Washington in Seattle. What are your thoughts on the implications of this discovery? Do you believe it could lead to a breakthrough in understanding the matter-antimatter imbalance in the universe? Share your opinions in the comments.